Our next speaker is Dr. Sae Woo Nam, who's been a staff scientist at NIST for more than 15 years. He's one of the pioneers in single photon detectors. He started his work in transition net sensors, but has moved gradually into superconducting nanowire single photon detectors. And he's going to be talking today about one of the results that actually got all the CQP more excited, the gravitational waves, which is the proof of loophole-free Bell inequalities. So whenever you're ready.
All right. Is the microphone working? Oh, it sounds like it's working. Okay. So first, let me thank the organizers and Mark for inviting me. It's been a very stimulating workshop conference to hear all these ideas from all these different parts of quantum information and quantum computing. So I really appreciate the opportunity to come and actually speak to everyone here. And hopefully from my talk, whether you're a theorist or an experimentalist or a photonic person or quantum dot person or superconducting qubit person, there'll be elements in here that may interest you because the experiment we did combines a lot of things from a lot of different fields and hopefully even could generate interest in the industrial community about how one can use Bell test measurements for maybe a new kind of application. And so the original title I had was Hardware for Loophole-free Bell Tests Using Photons. But really the reason we're doing that and why we started this project at NIST was not to actually do a loophole-free test. We didn't actually think we would ever be one of the first groups to do this. But we started a program around 3 years ago to investigate whether it's really possible. I mean, you read these theory papers, quantum information theory papers, and people have all these interesting ideas. And one of the really interesting things is to generate random numbers. And one of the things we wanted to understand is that really possible? Can you realistically, in some sense, certify the quality of a random number in some really quantitative way, and then put it in a beacon where it's available for people to use? So this started 3 years ago. We're 3 years into the project. We happened to do a loophole-free Bell test. The loophole-free part isn't quite necessary, but we realized 3 years into or 2.5 years into it that, well, we just separate these things and maybe we'll be one of the first groups to do a loophole-free Bell test. All right, so here's a brief outline of what I'm going to talk about. I'll just maybe motivate briefly why a random number beacon might be interesting. I'll describe our experiment that we tried to do and what were the key technological advances that really enabled us to do this. What are the remaining challenges to take that Bell test measurement apparatus and actually try to get random numbers out of it. And then maybe conjecture a little bit about where the hardware and technology could go. All right, so for those of you who don't really know about NIST, I mean, a lot of people probably have heard about the institution, but there's some things you may not know about it. So of course, one of the really important things at NIST is about advancing measurement science. And quantum information and looking at quantum systems, people have recognized as a very good way to improve our capability at doing measurement. And NIST actually has a long history, and the metrology institutes around the world, especially in Germany and in the UK, have a history of actually using quantum effects for standards, for advanced measurements. And one of the very first things that was used that required, in some sense, a quantum explanation was the use of black body radiation to help define the temperature scale. We of course don't do that today. It's defined a little bit differently, but that was one of the first uses of requiring quantum mechanics to explain some effect we want to use for some kind of standard. And the other really important thing about NIST and other NMIs is we feel very strongly about the integrity of our institution. We want to have the right answer. We want to measure it correctly. But what's not actually commonly known about NIST, which is a little bit different than other national metrology institutes around the world, is we're also responsible for setting some cryptographic standards for use by commerce. So in the US, there are two entities in some sense that handle cryptography science. One is, of course, the NSA. They handle that for the intelligence community and the Defense Department, and the other institution is NIST, and we handle that for the commercial entities, so they don't have to have expert cryptographers to understand how they need to secure, let's say, their banking commerce or things like that. We have some standards and standard practices that people should follow to have secure communications. And this idea of using random number generators or trying to create a new kind of random number generator really feeds into this mission of trying to provide better cryptographic standards. So this is a little bit of the motivation. It's a little bit old in terms of some of the data, but really, recently there's been a lot of attacks on our cryptographic resources that we use. Within the US government, we all carry these RSA tokens to log into the IT systems, and recently this was compromised. And so everybody had to turn in their little token and get a new one, right? And we don't want to have to do that. We want a better way to do that. And one of the primitives that, if you talk to different cryptographers, that people assume, one of the things you assume when you're doing cryptography is that there's no provable source of random number generators. You can't assume that your random number generator is good, right? It could be compromised. And so one of the ideas that we want to try to maybe change in that field is maybe there is a way to prove that the random numbers are really unknown by anyone beforehand. Right? You just don't know what these numbers are going to be until you get this, let's say, beacon or timestamped randomness from maybe NIST or maybe Microsoft will try to do this, maybe Google, I don't know, maybe IBM. Maybe they'll provide random numbers that are certified in some way via Bell tests, via very good measurements of different quantum states. All right, so the reason we want to do that, really, what's really important about these random number generators is, and I don't mean to criticize this really good product actually by our colleagues at ID Quantique. They have a really nice quantum-based random number generator. But if you're really super paranoid, you don't actually know if some third party actually programmed in all the random numbers that you are going to get out of the machine that you bought. Because it will look random. It'll pass all kinds of randomness tests, whether you use the NIST test or the die-hard test or whatever. So it's possible, potentially then, with quantum mechanics and using the right quantum states, that maybe you could, use the fact that you've done a loophole-free test to ensure that no one knew what the numbers you were going to get beforehand. And we're going to rely on notions of like device independent security and things like that. And things like we heard about yesterday in terms of verification of quantum systems. All right, so one of the things that actually exists now, and I guess I forgot to put this on this slide, was if you go to beacon.nist.gov, there actually is a version of a random number generator that's available for you to get random numbers. And there's all kinds of caveats about not to use this for cryptographic applications. It's just really a test system to see what the interest is around the world in terms of getting access to random numbers. It generates about 512 bits of randomness every minute. Right, so that gives you the scale at which we're trying to generate, the rate at which we're trying to generate random numbers. And they're certified with different timestamps and digitally signed to make sure that it actually came from NIST. So that's already up and running. And what we're hoping is that a quantum-based system could then feed into that beacon and be a source of randomness that's provided to the community. All right, and so there are different cryptographic potential applications. I don't know the details of how the different cryptographic protocols work, but you can imagine, in some sense, trying to, with this new kind of primitive of truly random numbers that no one knows beforehand, there are ideas that the way you could authenticate or the way you could validate something could be a lot simpler. Wouldn't take as much computational resource. And certainly if you don't trust NIST, what you could do, if you could set up your own beacon, and you could exclusively OR your random numbers with someone else's random bits, and you'd get, protected randomness in some sense. All right, so one of the first things one needs to think about in terms of trying to do this kind of experiment is picking a quantum system or qubit system to try to do the measurements in. And at NIST, there are there are a lot of really smart people. You have Dave Wineland doing trapped ions, or Chris Monroe. And actually, Chris Monroe actually did an experiment where he showed basically generating 42 random bits per month with his trapped ion system. And that really isn't at a speed that we would want for the random number beacon. So our group decided we would try to propose to do something with photons to see if we can get that rate of generation of certified randomness up to even higher speeds. So to try to meet that 512 bits per minute. All right, so probably everyone in the audience knows something about Bell tests and how one does that. And so there's some key things. Of course, there's your source of entangled pairs. And what you want to do is generate your pairs, and while the pairs are in flight, let's say, to another location or where they're going to go, you decide randomly how to measure them. So it's important that the pairs exist. After the pairs are created in this, if you look in the space-time diagram, you want to decide how to measure them, eventually measure them, but make sure that the information about how measurements were done on one side can't reach the other side before you complete your measurement. So this is the kind of space-time diagram you need to try to ensure that your test is loophole-free. And then there's this nice article by Yanaki Larson in 2014 that kind of defines the standard loopholes that exist when you try to do this kind of experiment. All right, and so at the end of last year, actually, 3 groups around the world actually finally did this experiment where we basically closed all the well-known loopholes. And one of the things that one needs to be careful about is, certainly in the title of our experiment, we were very careful, and we chose our title really carefully. And each one of these words have a very specific meaning. Like the phrase local realism, we tried to be very careful about how we define that. One of the things is, what is really meant by loophole? And the short answer to that is any assumption you make about how things work. We try to make the fewest amount of assumptions possible. And strong, that really means we have very strong statistical evidence that it's unlikely that local realism could explain our data. And so there was a lot of theory that went into how to figure out how strong a result we had. It's different than what was, let's say, done previously in the field, which is I measure some Bell parameter, some inequality. It's bigger than 2. It's bigger than 2 by 5 standard deviations. Yes, that's what the field did, and that's what it's done for a long time, but that may not, I don't think that's the right way to try to analyze how well the experiment works or how good the violation is. It has no meaning, because why do you expect the errors or the uncertainties in the experiment to be Gaussian distributed? So why characterize it with a Gaussian when you don't even know what that distribution looks like? All right, so, one of the things that really, in the end, that made this possible was we had a lot of fantastic people that came together with the same goal. And we couldn't have done it as quickly as we did without actually having some really good people solving really tough technical problems. And so I would say these are, in some sense, are the key technical advances that we made. Some of it's hardware, right? So, if you're a photonic person, you've probably spent time trying to figure out how to make a good photon source of some kind. And so we spent a lot of time and figured out a good way to make a really high quality photonic entangled source of photons. As was mentioned in the introduction, we're at NIST. We have a lot of background in superconducting devices. Turns out we've, over the years, gotten really good at making detectors and making them extremely efficient so that one could think about closing the detection loophole with our kinds of detectors. The other thing, which, it's maybe a little bit more difficult to publish, is actually how do you move your optical components around? How do you move your lenses around? Where do you put your lenses so that you get reproducible, really high efficient throughput fiber coupling? How do you go from free space to fiber to free space with very low loss? And actually, one of the key people who did this was a student at the time, but he is in the audience. He's now working at Paderborn. Is Evan Myers-Scott. I don't know where he is, but he was important. He figured this out. Without him, maybe about a year ago when he did this, we would never have thought we could do this experiment without the work that he did there. And then being at NIST and really wanting to do the statistical analysis carefully, there was a lot of work trying to understand how to take the clicks that you see in your detector and translate that into some kind of measure of a probability that local realism could have explained our data, or could have explained our data more extremely. So computing what's commonly known as a p-value. And as a result of this, a lot of good people and a lot of good engineering, we were really able to get this really nice result. All right, so let me first talk about the source. I don't have much time to really elaborate on the source before lunch here, but you can go to this website, which is basically a calculator. It's a web app, and it will calculate for you a lot of different properties about how to generate a spontaneous parametric down conversion source, or a pair source of photons, based on different kinds of crystals. Maybe you're going to use a periodically poled material. You can put in the polling parameters, and it will calculate what you should get out of your source. It will calculate for you how well you'll be able to couple it into fiber. It can do a lot of different things. And it really, it was led by Christer Shalm, who was the first author on our paper. He led actually a group of people around the world who had input into this program, and making sure that you can actually calculate something and see basically match it to what you see in the lab. That really didn't, versions of this existed around the world in various research groups, but he did a good job at just trying to get people to work on this so that it's something that is publicly available for anyone to use. So if you're doing photonics and you're doing a down conversion source, I suggest you look at this and, see if the results that you see in the lab match. And if they don't match, feel free to contact us and we can figure out what's going on, whether there's a bug in our code or whether, it turns out there's an interesting thing that you may have overlooked in your experiment trying to make down conversion sources. All right. So the key thing for us is actually we were able to use that software, that tool, to really calculate how to get, how good a down conversion source can we get from our periodically poled KTP crystal. But the second thing really was then, okay, it's one thing to make these pairs of photons, but it's a second thing to make them entangled. And so one of the key innovations, I would say, was to use a polarization beam displacers, or a set of them, to actually construct the interferometer that you need to create the entanglement. And it turns out that there are other designs. The other optical photon experiment uses a Sagnac loop in Vienna. That's a good design as well. But we chose this beam displacer technique, and that really turns out to had been described earlier by the group at Oak Ridge National Labs. And what I would have to say about this kind of optical source is that it's extremely stable. We didn't know at the time when we tried to make it that it'd be extremely stable, but it turns out it is. And we turned off our experiment while we were writing our paper. We turn it back on, and it's still basically aligned. So there was like a 2-month period where we didn't do anything. You walk away for 2 months, you come back in 2 months on an optics table, it's still aligned. That's quite unusual, especially in this field. So it's quite a robust design. All right, and then the other thing, of course, is having really efficient detectors. We use superconducting-based detectors, these so-called nanowire devices, which I don't really have time to describe how they work. But in the end, we are able to make detectors whose system detection efficiency is above 90%. So what I mean by system is, if you have a photon and you've got it in the fiber at room temperature, there's better than a 90% probability we'll then see a click coming out of the device once the photon goes into the fiber, into the fridge, and hits our detector. So that's in some sense, that's the number you care about, is what is the detection efficiency when you try to use it in an experiment. You don't care about, well, after correcting for all the losses when I try to get the photon to the device, you don't care about that efficiency because that's not usable. You know, someone's corrected for all the losses that occur before it gets to the cryogenic environment. And so whenever we quote efficiencies for our superconducting systems, we always talk about the system when you try to use it, and it's above 90%. And then, of course, we've done some work to package it so it can just sit in a telecommunication rack, and you can just take it wherever you need to do your experiments. All right, so other hardware that was involved. One of the other key distinctions I would say about our experiment versus others is that we got a little bit paranoid about the random number generation. And yesterday, Morgan Mitchell was here. Unfortunately, I guess he had to leave, but he provided a random number generator for us. And turns out he provided a random number generator for all of the loophole-free experiments that were performed. And so you could say there's a Morgan Mitchell loophole, that everybody used his random number generator. So we tried to avoid that problem, and we actually had two more. We had an internal one that was made at NIST, and then we used a pseudo-random one, something that required, you know, that hashed together episodes of Saved by the Bell, Back to the Future forward, Back to the Future 2 backwards. It's all described in our paper. But then, of course, there are other things like Pockle cells to change. This is the Pockle cell to change the state or the polarization state you're going to try to measure in. There are time taggers, there are amplifiers, things like that. So this is an example of the free space optics that were used then, and this is the Pockle cell to determine what measurement basis we're going to use. This is an example. You can see the bottom of the cryostat. This is the time tagger system we use, different bias electronics just sitting in the lab. Okay. Anyway, so for those of you who are more photonic aficionados, here are more numbers. We used a Ti-Sapphire laser pulsing at 80 megahertz. We actually only used a subset of those pulses because our Pockle cell couldn't run that fast, so the experiment was run at 100 kilohertz. Every 100 kilohertz, we had a different setting. And it was really only on for a 200 nanosecond window in terms of the measurement setting. The detector systems that we used had about a 90% efficiency. It turns out if you try to back out the coupling efficiency from the source to the detector, if you didn't have all these components in the middle, it was about 95% coupling efficiency of photons into our detector system. But then when you add all the losses that go into like going out of the fiber, from the source to a fiber, go whatever 100 meters or so to where Alice was, come out of the fiber, go through polarizers, go through the Pockle cell, go back into fiber. The overall coupling efficiency was about 75%, which was high enough for us to do this loophole-free test. So these are the interesting numbers. This is looking from the top of where the different stations were located. So the source is located here. We did not do a back-to-back layout like one would like to do because we didn't have the lab space. We were able to plead with people to give us whatever random labs were located at the ends of the building. So the source is here. Alice was on this end of the building. Bob was on that end. There's a little YouTube video you're welcome to look at, which walks you through basically the path that the photons took. So this is let's say a blueprint of these two wings of the building. The red is actually the path the fiber took. The black is the, as the crow flies, separation between the different points. And so let me just briefly, in some of the time remaining, talk about the analysis. What we did was we actually, we used basically a version of the CH inequality. In this equation, what I'm saying is that a plus indicates we detected something, 0 means we didn't. A sub 0 means, Alice was set to setting 0, Bob was set to setting 0. And in this case, the number of times we saw a click in each. This is an example of the number of times that Alice did not have a click and Bob had a click, but Alice was on setting 1 and Bob was on setting 0. So this is the inequality that we were going to check. All right, so what we're trying to do is we're not really testing quantum mechanics. This is maybe a popular misconception. What we're trying to show is that local realism does not explain the world that we live in. And what we're going to try to do is say, how confident are we that local realism doesn't explain the world? And so we're going to use this notion of a p-value. And this is directly pulled from Wikipedia. It's going to be the probability that, that one could obtain a result as extreme as what we got, or more extreme. So it's not the probability we got the result we saw. It's the probability that we got the result we saw or more extreme, all right? And we're going to make a hypothesis. We're going to make some hypothesis, which we're going to call the null hypothesis, that something is true, and this p-value is going to be very small. And that hypothesis or null hypothesis is going to be that local realism explains our result. Right? And it turns out, with the kind of experiment we did, computing the p-value can be mapped to the probability of flipping heads. It can be mapped to a coin flipping problem. And all those terms that we saw in that the CH violation equation I showed before, all those terms, when you add them together, that's going to correspond to the number of times we flip the coin. And the number of times you saw a click in Alice and a click in Bob when they were set to setting 0 is going to be the number of heads. And then local realism says the maximum probability of getting heads is 50%. You can't get more than 50%. And when you look at our results, and this is an example of one of the runs, we saw heads way more than 50% of the time. It doesn't seem like a lot more than 50% of the time, but when you actually do the binomial expansion and add up the probabilities, the probability you could see heads this many times or more is on the order of 10 to the minus 8, or 5.8 times 10 to the minus 9. So this is the notion of why it's such a strong violation. The probability of getting heads that many times, over 50% really, is really low. Or that many heads or more. The probability is quite low. All right, so we've done this loophole-free test. It's a great milestone to have achieved in terms of trying to figure out how to make good random numbers, but there's a lot of work left to do. There was a very nice Peronio paper that he used SH quantum states and said you could make random numbers, but we did CH. So there's need to adapt the proof of whether one can get using CH violations to see that. And our theorists who are working on this, they think they have a way of doing that. Another interesting question really is, it seems somewhat circular. We have to use randomness to do this Bell test measurement, and then we're going to say we're going to get randomness out of it. In some sense, distilling randomness to be more random. And so one has to think carefully about what do you need to know about the randomness? What are the different trust models one needs to consider when trying to certify that this randomness was not known by anyone else a priori? In some sense, it's this notion of certification. How do we certify it in a way that people are going to trust? So there's a lot of theory left to do for this kind of work. But then there's a lot of experimental work left. And one of the nice things is that people who want to use this system for providing random number generation, they're not so concerned about locality. It's not as important. For physicists, when we're trying to do this loophole-free test, this is really important. But when we want to use this, it's not so important for random number generation. And of course, we would love to do this experiment with a real Bell state. What I didn't really describe carefully is, because of the imperfections in our system, and to get the maximum violation or the lowest probability that a local realism theory could have explained our result, turned out for our noise and imperfections, it was not optimal to use a Bell state to do the measurement. We used it was still entangled, but barely. And so we would love to do a true, using one of the true Bell states to do this kind of measurement, and that's going to require higher efficiency detectors. So that's something we're working on and hopefully we'll come up with in the future. But I think there are other things to think about for the future. And one is to think about, if we don't really have to be space-like separated, how small can I make it? We're in Bristol. There's a big effort to do integrated photonics. Can we put this whole experiment onto a wafer. Let's say it's a 150 millimeter wafer. Or maybe could we make it a chip? Can we make a 1 centimeter by 1 centimeter chip? I think that's an interesting question. And of course, we're working in that direction. We're thinking about it. This is an example of some work we did with our colleagues just across the street at the University of Colorado, where we were able to take some chips that were actually made in a commercial foundry. The same foundry that produces the chips for Watson, or if you have a PlayStation 3, the chips where your chips that were the processor in your PlayStation 3, in that foundry where that processor was made, we had a chip made. It was these guys who made the chip had no idea it was going to be used for photonics, but with a little bit of processing afterwards on that chip that they made, we were able to show you could make a four-wave mixing pair source of photons with reasonable fidelity. The other thing that we've been working on then is, of course, trying to figure out how to get light in and on and off the chip. That's one of the things that I think our group is quite good at, is coming up with new ways to do that, maybe and package that in ways that is more scalable. So recently we've had some interesting results in terms of coupling light on and off photonic chips with detectors integrated on these waveguides, and this is an example of the count rate as a function of bias current, and you can see that you have this really nice plateau showing that the efficiency of the device has saturated. And then these are results of using, so these are standard curves one would see in the photonics community where you're characterizing the quality of, let's say, an unbalanced Mach-Zehnder or the quality of your ring filters or things like that. But actually what's different about this compared to what you'd see classically is the y-axis, instead of being power on a power meter, it just counts from our detector that's integrated on the waveguide. And you can see the 30 or 40 dB, or maybe 20 or 30 dB rejection in the filter, or the 20 or 30 dB dips in the Mach-Zehnder, and all of this has been measured with nanowire detectors integrated on the waveguide. All right, so that's trying to make things smaller just from a photonics optical circuit point of view. And then the other thing I'm really interested in is more advanced cryogenics. I really want to see, and we have a small research program in this direction, I want to see the cryogenic field advance to the point where it's invisible, that the end user has no idea that the experiment or the detector uses cryogenics, is cooling to 1 Kelvin, right? And so the idea is basically, for those of you who do microwaves or use microwave sources, when you pick up that Keysight or Agilent microwave generator, if you aren't prepared, it weighs like 50 pounds. It's really heavy. And that's the idea. It's in this rack-mounted thing, maybe 6U high, maybe 9U, but hopefully 6U high. It takes only 300 watts. But it cools the detector and the chips, the photonic chips inside of it, down to a cold enough temperature. It can just sit in a rack, you give it electricity, and it just runs. So we have a design. We're in the middle of constructing a prototype. But I'm hoping to have this invisible cryogenics for these photonic type experiments. The time tagger hardware, that's something I think classical computing is getting faster. We just completed an upgrade where we're no longer using, let's say, a PC or an Intel PC to run the experiment, but we're using something like a Raspberry Pi class computer in combination with an FPGA to do the time tagging. All right, so let me just end by saying I'm lucky enough actually to represent a huge group of people at NIST and the different people from different institutions that worked with us to do this Bell test experiment. And actually, I think it's a privilege to be able to work with such good people at NIST. So thank you for your time and attention.
So we have time for a few questions. What is the threshold for the Bell test experiments? What is the threshold on efficiency?
Oh, okay, so if there were no imperfections, there's a paper by Eberhard, and it's 2/3, right? If we didn't have any dark noise or anything, things were perfect, it's 2/3. But because of imperfections and the fact you've got to attribute, let's say, these imperfection or errors to to someone, let's say a local realist, you need some margin. So we needed, for our experiment and our imperfections, I think it was something like 72%. So we had some margin there.
Thank you. So loophole-free bell tests have been done. I mean, obviously, there's still more work to be done, but that's a clear, big challenge that a lot of people were focused and driven towards. What do you see now as the next big challenge, other than building a quantum computer?
So yeah, you're right. This was a really big challenge. A lot of people were trying to do this. I think for me right now, I think if you think about like where quantum information, or maybe quantum information 2.0, that, you know, in the sense that entanglement or something, you want to use entanglement. I think what we want to see happen is see it move to the private sector, commercialization of some kind. And certainly QKD is already out in the market. And what I'm hoping to convince people, as well as my NIST colleagues who are more into the cryptography side of things, is suggest that this is an interesting thing in terms of helping us to have a more secure, let's say, cyber infrastructure, having random number generators that are provably secure. You know, our goal really with this project is to figure out ways to certify the randomness, publish all the blueprints. I mean, you could ask us now and we'll tell you everything, how we did everything. And you can come visit us and we'll show you everything about the experiment. We want people to duplicate it so that there can be beacons all over the place providing random number generation for people, and hopefully that can lead to a more secure internet, right? And hopefully companies will then either build their own, maybe they're little small startup companies that will build these systems for people. I want to see commercialization of some kind of little quantum widget on an early scale versus waiting for a quantum computer.
More questions?
I was wondering, you said that the state that you used in the end that turned out to be optimal for the violation was barely entangled. Could you say a bit more about what that state was and why it was optimal?
I think it was like, so the question was what was the state we used to do the loophole-free experiment? And I think it was like cosine of 16 degrees H plus sine of 16 degrees V. I think that was the state. So it wasn't near 45 degrees. And that's basically because if you look at this paper by Philip Eberhard, you know, you can see that to get the most margin in terms of violation, you need to go to this asymmetric state.
There was a question at the back somewhere.
Just picking up on your cryptography comments, can you comment on device-independent QKD? Because the biggest problems there were lost, and it seems like you guys have something to say now. Can you just comment on the possibilities for doing that in practice now?
Wait, I missed the first part of your question.
Picking up on the QKD and device-independent QKD, because loss was the big killer there, and it seems like you guys have been solving some of those problems. Can you comment on the possibilities now?
So, yeah. Okay, yes. So we did a lot of work on reducing the loss, but you know, one of the things one has to remember is if you want to plug into the existing fiber infrastructure to do long distance, let's say quantum key distribution terrestrially, there's about 0.2 dB loss per kilometer in the best fibers. So one of the things that would have to happen to really to do things, let's say in a device-independent QKD way, is to reduce that fiber loss. And you know, that's of course an area of research, but then that costs a lot of money, and it costs a lot of money to relay all that fiber. And I don't know if the payoff will be there commercially, but certainly it's potentially possible. The dominant loss is going to be that, I think, the fiber. But I think it's also quite interesting that, you know, people are trying to to pursue things like satellite QKD, and maybe in free space with really good optics and adaptive optics, one might be able to reduce the loss. But I haven't looked at that problem to really understand whether it's possible with free space to get that loss low enough so you could do a device-independent QKD. I think it's really hard. I think what Thaddeus is trying to do, I think that's potentially better. I think coming up with a scheme with repeaters is, I think, a smarter way to go.
Maybe a last quick question. I'll use my privilege of being here then to ask one question. So, as Thaddeus said, one of the disadvantages or ugliness of some other technologies is precisely the fact that they have to go to very low temperatures. Silicon photonics, or in general photonics, has not suffered from that too much, but now with these superconducting detectors that are essentially required, it seems that we joined the club of cryogenics for a long, long time. The question is there in perspective of leaving that club or reducing the requirements for cryogenics so it can be, as you suggested, integrated into a smaller and more practical device?
Yeah, so I think with a lot of things, the reason we go to cold temperatures is because the noise is lower. And part of the reason photonics really hasn't had to go to low temperature is the temperature of the photon we're trying to use is so hot compared to room temperature. The superconducting qubit guys are using microwaves. That's really cold relative to room temperature if you think about the effective temperature of that photon. And so I think there's potential. You cannot rule it out from fundamental physics that I know about that you cannot do really efficient detection at room temperature. But there hasn't been a strong driver to really fund research in that direction. And I think it's such, for me personally, it was such easy, low-hanging fruit to figure out how to make efficient photon detectors cryogenically. I just my background and what I knew about physics, I was like, oh, this is a trivial problem. I know exactly how to do this. So that's why we did it, and we have these nice detectors. But there is no fundamental reason that I know about that says you cannot do it at room temperature. But I know how to do it. There's low-hanging fruit in terms of, let's say, the Bell test that we were able to do as a result. And but hopefully there'll be people who try to make it more efficient semiconductor-based room temperature devices. And certainly John Rarity yesterday talked about that. You can get really efficient CCDs, right? That exists today. Right, and there's no reason why you can't expect that people eventually, with smarter people than me, will figure out how to make single photon detectors on that tell you right away that there was a single photon versus integrate.
Thank you. So I think that should close the session before lunch. Let's thank again Sae Woo.
Thank you.